Oh, 49 minutes left, so that's not so bad. The batteries keep going. Okay, so truth functions. Defining the five logical operators, we just did that. That's what I did first. And so you start off with negation. And it shows you that's pretty intuitive. P is true, and not P would be false. Whereas P being false, not P would be true. That's pretty intuitive, right? Notice the explanations, a statement form. What we're doing are statement forms. The argument form we haven't started yet, but we will in a moment. Substitution instances. Notice that we're talking about a statement form, so you could actually fill in for these. Any statement could be. It doesn't have to be Terry or Becky has a CD. You know, it could be any two statements connected by a disjunct there. So you can use different substitution instances. And we're building a truth table to talk about it. Conjunction is the dot operator, and you have that given to you on page 330. If you don't immediately remember these, if it's not intuitive to you, you might want to remember these pages to refer to them. Conjunction is page 330. Disjunct or disjunction is page 331. And the horseshoe or the conditional operator is also on page 331 at the bottom of the page. If you drive south on I-15, then you will get to Los Angeles. What if you're already south of Los Angeles? And the biconditional, or tribar, is defined on page 332. Right? And remember, that's it's true provided both the left and the right are the same. So if they're both true, then it's true. If they're both false, then it's false. It's only false if you have a mix between the left and the right. Okay, so operator truth tables in ordinary language. So if we're translating from ordinary language into these statement types, you have a variety of things you have to think about. So an example on page 335, Steve is an accountant and he lives in Omaha. So you could put A.O. If you wanted to say Steve lives in Omaha and he is an accountant, you could have O.A. Well, what happens if we construct truth tables for these? Since the truth of the left and the truth of the right could be different, the truth table for the two statements well, in this particular case, since, okay, I see what they're doing. So they turn out to be the same. They're equivalent. Doesn't matter which way you say it. Next page, 336. Shirley got her IRS refund this week and bought a new TV. So it's abbreviated I and T. So the I stands for Shirley got her IRS refund this week. And Shirley bought a new TV is T. I'm not sure why they keep switching them here. If Boston is in Alaska, then Boston is near the Mexican border. Clearly, that's meant to be funny. Most people would rightly consider this statement to be false. I'm not sure where they're going with that. Maybe if we do some exercises, that might be interesting. Page 339, exercise 7C, point 2. So for the following, let P be true, Q be false, R be true, and S be false. Determine the truth value of the compound propositions. So he's already giving you these values. Let's write them down. So P is true, Q is false, R is true, and S is false. Okay. So the first one he gives us is P and not Q. Well, P is true, and Q is false, but not Q would make it true. So P, so true and true, so in that case it would be true. And that's what he says in his version of it. See how that works? So the next one he gives us, this is one, next one he gives us is Q and not S. So Q is false, and S is false, but not S would make it true, but it's false and true, but that would be false. P then Q. So P is true, and Q is false. So true then false, that would be false. Remember, the only time that a conditional statement is false is when the left side is true and the right side is false. S or not Q. Number 4. S is false or not Q, which would be true, right? Because Q is false, so not Q would be true. So false or true, so number 4 is true. So how to do those? Because he's already giving you the truth value for all of them. In section 2 on page 340, it's the same type of thing. And he's saying let P be true, let Q be true, R be false, and S is unassigned. So the first one he gives you, if P then not Q, since P is true and not Q would be false, it's if P then false, so the whole thing should be false, which he gives us. 2 is Q and not S. So Q is true, not S? Well, we don't know what S is, so we won't know the answer to that one.
Well, if somebody asserts something to be true and they don't know that it is true, aren't they false? Aren't they wrong?
Well, in this case, we don't know what S is. And saying that it's false, that whatever, if S is true, saying it's false would be false, in which case 2 would be false. If S is false and not false would make it true, then 2 would be true. So not knowing what the truth value of S is means that we don't know what the truth value of that is. Now, by comparison though, if it had been a disjunct, then I already know enough about the compound statement's truth value to say that the whole thing is true because Q is true. But in this particular case, this was a conjunction. I need to know both sides of this. So I won't go otherwise. Let's look at a more complex one though. Number 11. So it says not P or parentheses, not the case S or not the case R. Okay, so my main operator in all of this, thinking inside of here, I have a compound statement not S or not R. So this is the main operator inside of here. But all of this is under the power of this connector here. So this is the main operator in that whole statement. So when I'm trying to figure out if this statement is true or false, this is the operator that will give me that value, whether it's true or false. But to find this out, I have to work it out from the beginning on the whole thing. So if P is true, not P will be false. S, I don't know what S is, right? So I don't know what not S is. R is false, but not false is true. True or whatever will be true, and it's true or whatever, so the whole thing is true. So I would know that the truth value of 11 is true. All because I know that this is true here, right? And it's this or this, right? And since this is true, this whole thing is true, and that makes the whole thing true. Okay, the next block, page 341, explains that little rule that I used, where you put the n for the number of variables you have. Notice they work this out. They call it for the L equals 2 to the n, where L is the number of lines, I guess, that you need. Computers can use that more than us. Okay, order of operations, if I'm trying to figure them out. I want to start from inside the smallest point and work my way out. So we first determine the truth values for each line under the dot. Let's do the same thing that they're doing here. So I'm trying to figure out for P and Q the value of this statement, and it's not the case. P and Q or Q. So how do I figure out what the truth value of this is? So which way does he line these up? True, true. So my main operator is here, because it's saying all of this or this. But before I can figure this value out, I have to figure out both what's over. This one is easy. I can just duplicate what I have for Q here. So I have Q, so I have the or this, and by the way, that means that the whole thing is going to be true here, and it's going to be true here. But for the whole statement, I have to figure out, well, what about these possibilities here and here? And so I'll look over at this and realize that, well, this negates whatever's in here, but before I can figure out what the negation does to this, I have to first figure this out. And so I look at P and Q and I'll say that, well, it's true in this case, but it will be false here, and false here. And then I negate it, so I have false, true, true, true. And now I'm looking, so on the first one I already know that the whole thing is true, and the same thing with the third one. But what about this one? Well, that's good. I have a true here, which means it'll be true there. And I have a true here, which means it'll be true here. So that's interesting. In all cases, this statement will always be true, which makes it a tautology. And I can try to figure, well, why would that be the case? Let's plug in something, instantiate something so it kind of makes sense, right, in order to think about it. So Jane is blonde, and Mary is brunette?
Yeah. You're right.
Red. I'll just go red. That's many of us. Okay. Or Mary is red. Okay. So it goes. It's not the case that Jane is blonde and Mary is red, or Mary is red. Well, if you think about it, if Mary isn't red, then this side would be true in at least some of the cases, right? But if Mary is red, so we've got Mary not red, right? Well, Mary is red. Now, if I were just to say either Mary is red or Mary is not red, you'd notice that that would always be true. So in a sense, that has snuck through this more complex statement, because we've added just for fun, we've added the issue of, say, Jane is blonde, right? So it's not the case that Jane is blonde and Mary is red, or Mary is red. When you get right down to it, I'm looking at, well, either Mary isn't red or she is red, right? So no wonder it turns out, the statement turns out to be true all the time. But that's just fun. So that, because it works out to be true all the time, you could put anything in there, and the statement form makes it true all the time. The statement form is a tautology. So, remember when it said only AEIO statements are true or false, right? And that's in the sense where, like, I'm saying this is a cup, things of that sort. But remember, when we have compound statements of statements that are true or false, you can have forms that will always be true, tautologies. AEIO statements will not be tautologies or contradictories. They're always contingent, because in order for an AEIO statement to be true or false, we have to see whether it's right or not, right? So it's this is a black magic marker. That's true, right? If I said this is a black magic marker, that's false, right? You see how that works, right? So when we're talking about an AEIO statement, which is like the baseline of where we begin saying we have true or false, right? So AEIO statements are determined by their being right. So they're contingent on the situation, right? But when we put a statement together in a particular form that makes it always true, in which case it's a tautology, or it's always false, in which case the whole, so I could put a bracket around this whole thing and put a negation out in front of it, and as a result of that, it would always be false under all possibilities. So I just turned a tautology into a contradiction, right? So this form will always be false, no matter what you substitute for P and Q, as long as you substitute the same things for P and Q in all the places, right? And keep the form correct, right? So how do you say then that AEIO statements are the only statement types that are true or false? But at the same time, keep in mind that when you get to compound statements of those, then you can have statements that are true all the time, statements that are false all the time, but they're made up of compounds of AEIO statements. Right? You wouldn't say, it's not the case that yippee and how old are you? Right? No, those are not true or false, right? Right. So you notice you're still looking at AEIO statements in there. Okay. Am I going too slow? Or is this, does this make sense? It's okay? I can go faster? No, can't go faster. Okay.
Still wrapping my mind around it.
That looks pretty twisted, actually. Yeah. Well, have you ever seen one? They're like,
Brain?
yeah. How the heck do you manage when your brain looks like that? Okay. So, page 347, contingent and non-contingent statements. I guess this is where the book says better what I just tried to say, right? So contingent statements are statements that are neither necessarily true nor necessarily false. They are sometimes true, sometimes false. They're contingent on the situation being the case. This is a black magic marker. So if we're looking at P or Q, depending on what you mean, well, yeah, I mean that is going to be contingent on P or Q. But here, the very next statement type is a tautology. So P or not P, for example, that's P or not P, which was what essentially we were set up for in that last statement, where I instantiated Mary as a redhead. Right. P or not P. We don't have any redheads in the class present? Oh, well. So I'm pretty attached to red myself, because even though I don't have red hair, when you look at my family, tons of them are red-haired freckles, which means we're loaded with Neanderthals. So I love that. That's just so neat. When I learned that Neanderthals were where we get the Caucasian red-haired, red freckles, I thought, that's cool, because we always made fun of Neanderthals. Even the, what commercial was it? The insurance commercial, Geico? Geico? Right? The poor guy. I love the commercial. You know, where he's going through the airport and he goes by the sign and it says, "Even cavemen can do it," or something, right? And he's like furious, because he's offended, triggered. Yeah. I still hear the music. It's real airport music too. Da, 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 da. And he's, you know the commercial.
Yes.
Right? It's just hilarious. However, so I feel a connection, but tautology. But so when I look at this, I only need one variable for my truth table, because it's either true or it's false. And in the case where P is true, not P is false. In the case where P is false, not P is true. And so in this case, it's true. And in this case, it's true. So it's a tautology. It will the form of the statement, no matter what you put in for P, will always be true. And you could just, one way you could form a contradiction is to just go like this and say not the case, because then it would be false and false, right? Or, as you see on the next page, you could form a contradiction by just changing this P and not P, which would always be false, because remember, this requires both the left and the right to be true, but in this case it will always end up being false. So this is a contradiction. You can't say that. Okay. Next section, logical equivalence and contradictory, consistent, and inconsistent statements. So logical equivalence. When we say that something is logically equivalent, we say that two truth functional statements that have identical truth tables under the main operator. When this occurs, they are logically equivalent. And I actually showed you one of those already when I said that this is logically equivalent to this. Right? We could also say that when we say P then Q and Q then P is logically equivalent to this. I should actually show you that one. Let's do that. So, thank goodness there are 4. You never have all 4 of them at once. That would be, because I've reached that shape now where gravity is no longer my friend. No. Okay. So if P then Q, true, P then Q will be false, P then Q will be true. If Q then P. Now if I'm trying to figure out what the truth value of this statement is, looking at this table, I'm going if Q then P. So if true then true. If false then true, that's true. If true then false, that's the one case where it will be false. And if false then false, true. Right? And then I'm looking at conjoining that, and so I have true here, false here, and true here. Right? So this whole statement is true in this case and this case. By definition, this one is true here, false here, and true here. So if I compare this with this, notice this whole statement is logically equivalent to this statement. So this is true for all these cases, right? I could just draw that line or just say 1, 2, 3, 4, right? Because is this true? Well, true, it is true. False, well that's the same, right? So that's true. False, that's the same. So it's true. And true, it's the same, so true. Right? So this is logically equivalent to this. You look confused.
Still wrapping my head around it. Like I said, it's
See, this is where computers pick up speed and do all this work for us, so we don't have to.
So there's no operator between P and Q. Is that part of the?
Oh, over here?
equation? Yeah.
This is my truth table.
Okay, I got
In
you.
other words, I have these here with no operators, because I'm just saying, okay, under the circumstances where P is true and Q is true. What about the case where P is true but Q is false? Oh, and then we could have P false and Q true. Or we could have both of them false. So this is my table. These are my statement forms. And I'm using the table as my guide for what I've got going on over here. So I'm looking at if P, then Q. right? Well, what is P? Well, in this case, it's true, and Q is true. So I put a true there, right? In this case, now, if P then Q, Q is true, but Q is false. And in the situation where I have a conditional statement, where the left is true and the right is false, then the statement is false. Right? So I'm figuring out what the value, the truth value of this is based on this truth table.
I got you.
And then I looked at this one, trying to figure out what's the truth value of this statement under the same truth table, right? And notice that because this is if P then Q, but this is if Q then P,
Okay.
this is different. These are different, right? Because for true then true, it's the same. But in this case, it's if false then true. Well, that's true for this one. Remember, for this one, though, I was going the other way. And so that was false, right? Here, now I am going the other way, right? If true then false. So that's false here, while it was, this one was true. So the same truth table, these two statements are not logically equivalent, as you can see here. Here it's true, here this one's false, this one's true, here this one's true, this one's false, and here both of them are true, right?
Okay.
So I can figure out what these state, and then I can go to the next step and say, well, and then this is a conjunction. Because what this statement says is, if P then Q, and if Q then P, that's this. And then still further, of course, it says, if P then Q and if Q then P, then if P and only if, or P if and only if Q, right? So we're saying the whole thing.
Okay.
I don't know if I did that well enough or not.
As far as
Because the way you read this is if and only if. So if and only if this is equivalent to this, but it is.
So in drawing out your table, as long as you can make one line across where it's all true, then it's a true statement. Well, that
So I'm looking for the main operator.
Yeah.
What's the truth value of the main operator? In this whole thing, the main operator is right here. Because it's relating this thing to this thing.
Right. Okay.
But on this side, the main operator between all of this is right here. But before I could figure that out, I had to figure out the ones on the sides. Because this operator says I have to have true on both sides
Right.
for this to be true. But what is on this side? Well, this is if P then Q. So I have to figure out. I mean, our everyday speech can be quite complex. We use lots of comments that include, at base we have statements that are true or false, but we add them to one another, or we disjunct them with one another, or we conditionally state them, right, as we do. So we could very easily use this symbolic system to look at very complex statement types. I mean, you know, we can talk about P and Q. That's any conjunction you make. That's two statements that are true or false. But then, you know, I could get more and more complex as I go. And I don't just have to look to the IRS, you know, directions to do that. I mean, you know, part of the problem of the meeting on the 5th of July is they're trying to figure out whether the legislator has to go where the governor said that they have to go, or whether the law allows them to decide where to go. So you've got a whole bunch of people reading the legislation that decides which way it has to go, and they're reading it and trying to puzzle it out. Can the legislature decide not to go to Wasilla? They say we should go to Juneau or Anchorage. And the governor says, if you don't show up in Wasilla, I'm going to send the police to go arrest you and bring you out to Wasilla. He said that. He said that.
That works if they're skipping session. Like if you had a session and then someone didn't show up, then he would have the authority to do that. I'm pretty sure that's how it works.
Right,
in
but
almost
what
every
if
state.
he told them to have the session in Wasilla and he goes to meet them
they
and they're not
decided
there?
To have the section in Anchorage.
Yeah,
As long as they decided unilaterally, wouldn't that be an overreach of executive power?
that's what they're trying to figure out. But I mean, if you think about it, you've got people that are sitting there using, I would think, you know, this kind of attempt to analyze what's in the documents to figure out who can say what, who can decide where they all have to show up. And it could be confusing because, you know, some seem. I think the real reason it was confusing is because no one ever before decided to meet in two different places. You know, it was always the case that when they were trying to decide whether to have a special session or not, okay, the governor would call for a special session and everybody would show up where they're supposed to show up. But this time he picked a spot and they don't want to go there. That's, as far as I can tell, that's never happened before. So they're all going back to the books trying to figure out who can decide where the meeting should be. Does that make sense? But what are they doing? They're looking at, well, this and or that. You know, which comes first? They're doing the same kind of analysis of the truth value of the statement. Which I think is,
What dictates that? Is that the Constitution of them? Or is that just
well, it's the
bylaw?
laws that were written.
So it's laws,
Yeah.
it's not.
Yeah. And just like anything else, just as I've said before, we're making this up as we go. So these lawmakers are making this stuff up. They're trying to figure out, well, what did we make up here, right? How are we going to decide this, right?
Not all of it's made up. I mean, yeah, procedures aren't made up. You don't just make up procedures. I mean, at some point they may have been that way, sure. But
Well, if you follow, it's not Murphy's Law, it's the rules of I can't think of the name of the rule book. There's a rule book on how you hold a meeting.
etiquette? Are you referring to etiquette?
It's not etiquette. No,
It's not
it's a book. I've
Minutes?
well, the book that tells you how to keep the minutes. There's a book. Robert's Rules.
Yeah, Robert's Rules of Order.
Robert's Rules.
Robert's Rules of Order. What's that about?
You've never heard of Robert's Rules?
No?
How to,
How to have a meeting.
yeah.
Oh, really?
And as far as I know, everybody,
Everybody?
follows Robert's rules.
All M is B.
All M is P. Yeah. There you go. So when you worked for the NSA, did they ever give you like a cyanide pill to take if you were captured?
Nope.
He couldn't tell you anyway.
We did learn the expression though, "Ni streljaje et ja ani udka." Don't shoot, it's me and not a duck.
That is funny. That is very funny.
And we also learned that if the balloon ever went up, we could put on an outfit and take a broom and go out and sweep the street. And as we saw the Russians coming, we would say, "Na zapad, na zapad," which means go west, go west.
Why would you say that?
So they wouldn't arrest me. They would keep going.
Oh my gosh. Wow. That's crazy.
That was just a joke. We never had to do that.
Oh, you never had to do that.
But you were ready.
Yeah, what we heard was if the balloon ever did go up, the Marines were tasked with shooting us first. That's not very nice.
Wait, what? Wait, are you being sarcastic again, or are you being real?
I hope we were being sarcastic, but that's what they told us.
Oh, that's... wow.
I'm sure I did everything right. It's just, aha, there it is.
Those are famous last words,
Aha, there it is.
I'm sure I've done everything right.
Oh, I'm sure I did everything right. That's really horrible.
So, yeah, if you're in any kind of committee or
Organization.
and the legislature uses it too, if you ever watch them on TV and you see how they refer to whoever is in charge of the meeting, etc., they're following these rules. Well, this doesn't actually... Let's see if Wikipedia maybe will just... But yeah, that's how meetings run. And it's kind of helpful whenever you have someone at various meetings who knows the rules by heart, or well enough at least to tell you if you're doing it right. Because even if you're like the president and you're trying to run the meeting and you don't know how the rules go, you don't know how the questions can be presented, how you have to follow the agenda, all people that have, want to argue about things, but are they in order or not? You have to keep it very strict, otherwise the whole meeting just goes to pot and nothing happens right. So yeah, so those rules actually are really important. And we end up with the same logical process. When you analyze the rules, the guy that knows, or the gal that knows the rules, how things should run, and so the person that says, I want to ask a question here, oh, you can't ask that. This is the one that's on the table right now. We have to solve this first. Then we could look, for...
And then you make a motion to such and such, a motion to
Mhm.
either change it or remove it.
We have to vote on this before we can go to anything else.
All in favor, aye or
Mhm.
nay.
Mhm. But if you think about it, the person that knows the rules knows the sequence. So you're looking at that same kind of thing that we're doing right now when we're looking at the way you figure out the truth value of a statement. He's looking at the logical process by which this has to happen first, then this can happen.
Right.
Right? You're putting that same kind of thing together.
Like, you've seen the visual diagram where you can follow it. If this is true, then do this. If not, go here. You know what I'm saying? Like, I can't remember the name of that
A
diagram.
decision tree?
Is that what it is? I think so.
Yeah, I think that's a decision tree.
Decision tree.
Decision tree.
Everywhere I go, there's always something to remind me of another place and time.
Thanks for watching a video from the
Plus, the Neanderthal was doing a OK symbol, which is controversial now.
What?
Oh, was it?
The OK symbol, or the circle game, as
How's that controversial?
so the story as I know it is on 4chan there was an attempt to, I guess, troll those that get offended really well or really easily, thinking it's a white power symbol by the W and the P, like you can
Oh
make
my
the letters.
gosh. Okay.
And then now,
You know that? Oh, that was all over the news.
and then, so even, I mean, it's going pretty far. Like a spectator at a sporting event did this symbol behind a news commentator, but it was upside down, like the circle game, and he was banned from anything. Yeah, it's getting a little sensitive, you could say, unfortunately. Because they don't know the meaning, like his intention behind that, but yet they said, you're never allowed here again. Which is pretty crazy to me.
The speaker I saw Sunday morning at 9 o'clock sells seeds, organic seeds, that she grows in western New York State. She has a company where they grow certified organic seeds. So you could buy them in seed packets, etc. And they're connected with Cornell University. But she kept referring to herself as Bouge, which I guess is the new version of bourgeois.
I've heard of bougie, like someone's bougie.
Bougie.
I can't remember what it means.
Well,
There's always
Bourgeois.
been abbreviations for French words, I'm sure. I mean, they're already cutting off half the word, why not cut off more? I mean, soon it'll be boo.
my one daughter, when she was young, she would see the word and she would pronounce it Burgoyce.
Burgoyce.
Burgoyce. But
Isn't that how we ended up with English? We just mispronounced French.
or mispronunciated it. Yeah. Especially if you put the emphasis on the wrong syllable. It screws everybody up. So, moving right along. Page 349. Logical equivalence. Actually, I already talked about that because that's logically equivalent. So we could look at exercises, the exercises on page 351. Use truth tables to determine whether any of the pairs of statements are logically equivalent or not. And they give you the first one. And so what we've got is this kind of crash bar in between the two. So that it says, okay, so statement, not the case P and Q. Is that equivalent or not to not the case P or not Q? And when you look at the answer that they give you, notice that they're saying for the truth table PQ, right, that you see on the left, right, that the main operator for the statement on the left is going to be false, true, true, true. And the main operator for the statement on the right is going to be false, true, true, true. In other words, they're logically equivalent. So in other words, you can say it's not the case P and Q, or you can say it's not the case P or not the case Q, and those two statements are logically equivalent to one another. Makes no difference which format you use to say it, you're saying the same thing. You see it? And by the way, we have the list of all of those in the back. When you look on if you look at your little cover in the back of the book, which you don't have, I guess, you have the 10 replacement rules in the back, and 2 of those are called De Morgan's, and we have not the case P and Q is equivalent to not the case P or not Q, right? Which is the one that they just gave you here. And notice you could also go not the case P or Q, and that's equivalent to not the case P and not the case Q. Let me put those on the board to look at those for a minute and compare them.
Truth tables for propositional operators, was that? Okay.
Not the case P and Q, not the case P and then the other one is not the case P or Q. That's equivalent to not the case P and not the case Q. So when I'm looking at this, right, we're saying it's not the case that both P and Q. And that is equivalent to saying it's not the case P or not the case Q. So, in other words, I could have P or I could have Q, but I couldn't have both P and Q. So what this is saying is, it's not the case that I have both of them. It might be the case that I have neither of them, but in any case, I don't have both of them. Because I could have one. What this is saying is it's not the case that I have both of them. But in this one, it's saying it's not the case that I either have P or Q. So I don't have either of them. And so when you look at the equivalent statement, it says it's not the case that I have P, and it's not the case that I have Q. Right? So I don't have either of them. This says I don't have both of them. I might have one or the other. I just don't have both. And what's interesting is, of course, this is equivalent to this. And of course, this is equivalent to this. So these go back and forth. And the same thing with this one. This goes back and forth. But don't get confused and think that this can go this way,
I think
or
it's
vice versa. You can't go this way, right? But they go this way.
I think it's the distribution that I'm still wondering about, as far as it is not the case that P and Q, and how that's different than the
Than this one, or this. This isn't different than this. This is the same
Right.
as this.
Right.
And this is the same as this.
Right.
But these are different,
Mm-hmm.
because this is saying not both, and this one's saying not either.
Okay. Yeah, I'm probably just gonna have to practice on it a bit.
Well, these are the kinds of things that could be head twisters, even if you've practiced it,
Gotcha.
if that makes sense. But notice we have 10 replacement rules, and this is just one of them.
Fine.
That's De Morgan. Augustus De Morgan. I think he might even be in the book, but he's another interesting logician that discovered that. So that's his rule, replacement rule. Well,
What's still throwing me off a lot too is the for. Is there any kind of indicator of whether or not it's was it we said inclusive or exclusive? Because that makes all the difference in the world. You can have a candy bar or you can go to the store.
the way the wedge is used in the book is the inclusive use. So the exclusive use, even though that was brought up and discussed, so that you could see why the interpretation of our connector or is used in the inclusive sense, was only brought up to explain why we use it in the inclusive sense, but there's not an alternative, so the symbol doesn't have alternative interpretations depending on circumstances. It's always inclusive.
Okay. I think I just have to slam into my brain what inclusive or is. Then, and I think
Well, it's just you can have apple pie or you can have peach pie. Okay,
so you
I'm
can
fine
have
with that.
both,
You
so-
can have both, right?
So
It's very annoying, when you're, someone says, "Do you want spaghetti or ravioli?" Okay, they hate you for that, but you're literally answering the question. It's just unfair, because in that circumstance, they probably mean for you to pick one or the other, not both. But if they